Dear students, in this class we are going to discuss about kinematic equations for uniformly accelerated motion. Before going to discuss kinematic equations for uniformly accelerated motion, I am going to write the acceleration time graph for the situation which we have considered in the previous class. We have plotted position time graph, velocity time graph for the same situation. Today, just for 5 minutes, I am going to consider plotting acceleration time graph for the same situation. I think you are all familiar with that situation. A car or any body which starts from rest from the origin at t equal to 0, x equal to 0, it starts from origin, then it picks up its speed till 10 seconds say, and after 10 seconds it moves with uniform velocity till 20 seconds, brakes are applied, and at the end of 22 seconds after traveling certain distance, say 300 meter, the body stops or the car stops. For this we have plotted position time graph and velocity time graph. Today, to make our discussion complete, let us try to draw the acceleration time graph. You all know how to plot a graph. Okay, you will be plotting two variables, one versus the other. Here, as the name suggests, acceleration time graph. Acceleration time graph. It is also called as AT graph. A is acceleration, T is time. As the name suggests, a graph obtained by plotting acceleration versus time. So here, let it be y, let it be x, this is origin. I am going to plot acceleration along the vertical axis and the corresponding time along the horizontal axis. This is time, okay, time t in seconds. This is acceleration, okay, a in meter per second square. Okay, this is acceleration. Okay, the situation, for the situation, body starts from rest. Okay, this is the initial position. Two, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22 seconds. Okay, so here you can give values. This is plus positive y, so this is negative y. Okay, say 2, 4, 6, 8, 10, 12, which is in meter per second square, acceleration. Here negative axis -2, -4, -6, -8, like that. Okay, for the situation, car starts from rest till 10 seconds it picks up its speed, means its velocity increases but not uniformly. Imagine, velocity is increasing but not uniformly. When velocity increases, no doubt acceleration comes into picture, acceleration will be there, but velocity is not increasing uniformly. So what? No doubt acceleration is not constant, say acceleration is increasing, okay, till 10 seconds. Okay, till 10 seconds acceleration increases. All right, from 10 seconds to 20 seconds acceleration is 0. Why? Because the body moves with uniform speed for 20 seconds, from 10 to 20 seconds, for 10 seconds, from 10 to 20 seconds, 10 second interval, from 10 seconds to 20 seconds, body will be moving with uniform velocity, means uniform motion. The velocity is not changing. When velocity is not changing, no question of acceleration, acceleration is zero. That is the graph, acceleration time graph, acceleration is zero. If you go upwards, acceleration comes, okay. So when acceleration is zero, your point will be on the x-axis, that is time axis, like this is the point from here to here, the all points, that is graph will be like this. This is acceleration time graph. Why? Because acceleration is zero from 10 to 20 seconds. Then at the end of the 20 seconds, brakes are applied, so car will eventually stop. So at the end of 22 seconds, car will stop. When brakes are applied, car starts to move with decreasing velocity. Imagine car moves with uniform decrease in the velocity. When velocity decreases, body is said to have negative acceleration, or it is called as retardation, deceleration, any word. Okay, it is moving with negative acceleration, but point is clear. We have assumed that velocity decreases uniformly. When velocity decreases uniformly, acceleration will be negative here, but it is constant, not increasing, not decreasing. Acceleration is negative, which is constant somewhere here. Okay, say 8 minus 8 meter per second square. Okay, somewhere here from 20 to 22 seconds. Okay, this is the graph. From 20 to 22 seconds, acceleration is, say, minus 8 meter per second square. Acceleration is constant, which is negative. Why? Because when brakes are applied, body starts to move with decreasing velocity. That is the reason why acceleration is negative. As expected, only then car can stop. If velocity increases, okay, car won't stop. Okay, since velocity decreases, finally when its velocity becomes zero, car is said to or car comes to rest. Okay, this is acceleration time graph for the same situation. Seeing this graph, we can explain the entire situation. Car starts from origin, okay, till 10 seconds its velocity increases, but not uniformly. So that is the reason why acceleration is increasing. And from 10 to 20 seconds, acceleration is zero, means body is having uniform motion. And from 20 to 22 seconds, okay, car is having negative constant acceleration, means its velocity goes on decreases. Okay, so this is all about the acceleration time graph for the same situation. Okay, acceleration time graph. You are plotting acceleration versus time. That's all. This was the remaining concept in the previous discussion. We have plotted position time graph, xt graph, velocity time graph, vt graph, and now acceleration time graph, at graph for the same situation. Okay. So in today's class, as I mentioned, we are going to discuss about kinematic equations for uniformly accelerated motion. This section is very important as far as your examination is concerned. I think you may be knowing. So 5 marks theory questions will be coming. Concentrated on this area, kinematic equations for uniformly accelerated motion. You may like this session. So this is very simple and very interesting. We are going to use graphical method to solve kinematic equations for uniformly accelerated motion. Okay, so you can expect 5 marks theory question in this section. Let me write the side heading: kinematic equations for uniformly accelerated motion. So as we discussed earlier, acceleration can change as well. Acceleration of an object can change, but for our simplicity, throughout our discussion, we are going to consider uniformly accelerated bodies for our discussion. So kinematic equations for uniformly accelerated motion. So no doubt, equations. So these are simple set of equations for uniformly accelerated motion, which basically relates few quantities, namely initial velocity denoted by V naught, final velocity denoted by V, displacement denoted by X. Time t and acceleration a. We can derive three basic equations. They are popularly known as kinematic equations for uniformly accelerated motion, which relates these five physical quantities: initial velocity, final velocity, displacement, time and acceleration. Initial velocity is denoted by V naught or VO, V naught. Initial velocity, final velocity V, velocity is denoted by V. Okay, displacement X, time T, acceleration A. Okay. Kinematic equations for uniformly accelerated motion are derived using graphical method. Okay, using graphical method, we are going to draw the velocity time graph for the simple situation. Let me consider the situation like this. A body is moving on a straight road with uniform acceleration, constant acceleration. It has its initial velocity V naught. After certain time t, let its velocity becomes V. Traveling a displacement x, let A be the constant acceleration. Let me repeat. Consider a body which is moving with initial velocity V naught with constant acceleration A. After certain time t, its velocity becomes V. That is the reason why it is called as final velocity at the end of t seconds after traveling a displacement x. So in any way you can express. This is the starting consideration part. We must consider an object which is moving with initial velocity V naught with constant acceleration A. After certain time t, let x be the displacement of the object, and at the end of t seconds let v be its velocity. We call it as final velocity. For this situation, I am going to draw the velocity time graph. Then using that velocity time graph, we are going to derive three important equations. They are called as kinematic equations for uniformly accelerated motion. Now let me draw the velocity time graph. Okay, velocity time graph, velocity along the vertical axis and the corresponding time t in seconds along the x-axis. Body is moving with uniform acceleration and it has initial velocity v. Okay, so keeping that in your mind, body is not starting from the origin. It has its initial velocity. It can start from the origin, but no doubt, but it has initial velocity, say v naught. This is the initial velocity, because we cannot specify the position here, because it is not position time graph. This is velocity time graph. Initially at t equal to 0, let v naught be the velocity. That is the reason why it is called as initial velocity. And for t seconds, say for t seconds, body is moving, or we have considered the motion of the body for next t seconds from t equal to 0 to t equal to t. For next t seconds, body is moving with the constant acceleration a. Okay, so you all know the slope of the VT graph represents acceleration. Slope must be a constant, so no doubt you will get a straight line like this. Okay, so this is the Vt graph for the motion we considered. Okay, so this is the Vt graph. This is O, this is A, this is B. AB represents, okay, AB represents the entire motion. It has initial velocity V0 at the end of t seconds. Okay, its velocity becomes V. This is V0, and at the end of t seconds its velocity becomes V. This is final velocity, this is initial velocity. Okay. I'll call this point as D, this point as D, this point as C. O, A, B, this is D, this is C. You can give any letters, no problem. Okay, so this is the position time graph. AB is the position time graph which represents the considered motion. Okay, using this graphical method, using this Vt graph, we are going to derive three important equations for uniformly accelerated motion. They are called as kinematic equations for uniformly accelerated motion. I'll rub this and I'll start the derivation of three important equations: first equation, second equation, and third equation. Three equations. First equation, V equal to V0 plus EAT. First equation. Second equation, we are going to derive, okay, special case, X equal to V0 t plus half AT square. Third equation, V square equal to V0 square plus 2AX. We are going to derive these three equations. This is called as first equation, second equation, third equation. Yes, let us derive the first equation, V equal to V0 plus AT. Okay, how do you do? Very simple. Initial consider part you must tell. Then you must draw the velocity time graph like this. Then you are going to use one important property or one important feature of a Vt graph. You all know, we have discussed earlier, the slope of the Vt graph represents acceleration. That is what I am going to use. Slope of the Vt curve represents acceleration. The slope of the Vt graph represents acceleration. That is, slope equal to, so in the triangle you all know, so this is theta, okay, you can take tan of the theta, okay, tan of the theta is called as slope, it's not needed, but tan theta equal to, or slope equal to, opposite side for this theta, if you imagine, tan theta equal to opposite by adjacent, that is BC by AC, that is slope equal to BC by AC, correct? BC by AC. Okay, that is, you all know slope of the Vt curve represents acceleration. Therefore, slope equal to acceleration A equal to BC. You all know, from here to here, this is V. Okay, from here to here, V0. What about this? This will be V minus V0. I hope you're all very comfortable with this. From here to here, that is V, velocity. From here to here, initial velocity V0. Okay, what about this? This, that is V minus V0. This is V. This is V0. What about this? This will be V minus V0 is nothing but BC. That is V minus V0 divided by AC. AC is nothing but 0 to t, that is t seconds. Okay. Now if you cross multiply, A means A by 1. Okay, that is understood. If you cross multiply like this, okay, A into t or 1 into V minus V0, that is 1 into V minus V0 will be V minus V0 into equal to A into t. 1 into V minus V0 equal to A into t. That implies, okay, I will bring this side, V equal to V0 plus A into t. V equal to Okay, I have taken this to this V naught to right hand side, that becomes positive. I will keep V here, V equal to, this comes here, that is becomes plus V naught plus AT. V equal to V naught plus AT is called as first equation of motion, that is first kinematic equation, very important. V equal to V naught plus AT. Here V is final velocity, V naught is initial velocity, T is time, A is acceleration. So here displacement term X is missing, only 4 variables connected, V, V naught, A and T. Okay. This is how we are going to derive first equation of motion, V equal to V naught plus AT graphically. Now let me start second equation. I'll rub this. We are going to use this equation. Okay, we are going to substitute this equation in deriving second and third equation. Yes, let us start the derivation of second equation of motion, X equal to V naught T plus half AT square. Fine. So another feature of VT graph we are going to use, we have discussed already very important, it is not needed, not necessary to show theta. Okay. Another feature of a VT graph, the area under the VT graph represents the displacement. We know that area under VT curve represents the displacement over the interval. This is an important feature of a VT graph. We have discussed this. Area under the VT graph represents displacement. We know that. You write, we know that, or we have area under the VT curve represents displacement. Okay, let us calculate the area under the VT graph. VT graph is AB. Area under the VT graph with the time axis, this is the area. Correct? This is the area. This is VT graph AB. Area under the curve with the time axis, this much is the area. Correct? So that area OABD, it is a trapezium. Okay, you can use two methods. Initially, first method let me introduce. I'll express the area under the VT graph AB as area of the triangle ABC, this much area, plus area of the rectangle OACD, that is area under VT curve, that is area under the VT curve, equal to, how do you do? Area under the VT curve, full area is expressed as sum of the area of the triangle ABC and area of the rectangle OACD. Let me repeat. Area under the VT curve, this full area can be expressed as the sum of area of the triangle ABC and area of the rectangle OACD. That is area under the VT curve. We all know that represents displacement. Here the displacement is X. We all know. Area of the triangle, I'll write here. Area of the triangle. You all know, in elementary classes you might have studied area of the triangle ABC equal to half into base into height. That is half into base, let it be AC, into height BC. Correct? Half into base into height, that is half into, correct? This is base, this is height I have considered, half into AC into BC, that is AC is time, okay, into BC is V minus VO or V minus V naught, correct? AC is time, okay, T, and BC is V minus VO. Okay, I'll write here, area of the triangle is half into time into V minus VO plus area of the rectangle. So we all know area of the rectangle, area of the rectangle OACD equal to length into breadth, okay, length or base into height, 0 to t, that is t seconds, that is OD into OA. What is OD? OD is t into what is OA? OA is V0 into t. Yes, the area of the rectangle is V0 into t. Correct. X equal to, that is area under the VT curve is displacement, x equal to area of the triangle, yes, half into t into V minus V0 plus area of the rectangle is V0 into t. Yes, therefore x equal to, I'll write here V0 into t plus half into V minus V0 or V minus V0. From the first equation of motion, we have derived V equal to V0 plus AT, correct? V equal to V0 plus AT. Now if you bring this side, that implies V minus V0 equal to A into T, correct? Let me start. V minus V0 equal to A into T. Now substitute that star V minus V0 equal to AT here, half into T root T, and V minus V0 equal to A into T, correct? Yes, we have almost arrived. X equal to V0 T plus half into A into T, that is AT square. Therefore, X equal to V0 T plus half A T into T is T square. So, this is second equation of motion, very important. Okay, X equal to V0 T plus half AT square is the second equation or second kinematic equation for uniformly accelerated motion. Simple idea. We have used area under the VT curve represents displacement. Area under the VT curve is expressed like this, and using the first equation we could able to arrive the second important kinematic equation, x equal to V0 T plus half AT square. This is very important. As far as your examination is concerned, this question may be asked for 5 marks theory. Okay, if that question comes in the exam, you must write the the initial consideration part, then you must draw the VT curve like this, then area under the curve, follow the same steps, substitute that V minus V0 equal to AT from the first equation, you must mention, finally you arrive this step. Okay, you will get full 5 marks. Yes. Now let me derive the third equation, V square equal to V0 square plus 2AX. Don't get afraid of the derivations. These are all very, very simple. Just try to use your common sense. Okay, you try to give relations from one step to next step. That is actually all about the game. Okay, you don't mug up or you don't write the steps directly. You just draw the diagram and write the statement, then understand the statement, then follow the steps. So it will be very, very easy. Okay, let me rub. But for the third derivation, third equation, kinematic equation, V square equal to V0 square plus 2AX. The starting step consideration, consider part, diagram and area under the VT curve, everything same till here. Okay, till here you must repeat the same steps till here. Okay, now what you have to do is you just carry this step in this way. Okay, half into, okay, you just split half into T into V, that is half into V into T minus half into T into V0, correct? Half into V0 into T, correct? Half into V into T minus half into T into V0 or half into V0 into T plus V0 T, correct? Okay, so this is half into V0 T, this is V0 T, this is full V0 T, this is minus half into V0 T. This is 1 minus half of V0 T. 1 minus half is half. If you subtract half from 1, you will left half. 1 V0 T minus half V0 T. What you will get? You will get half plus half V0 T. I will write So this is only one term, no problem. Half into Vt, 1 V naught t minus half V naught t. That will be half V naught into t. So half is common, I will take outside, half into V, t is common, V plus V naught into t. This is x. Okay, this is one important step. Okay, x equal to half into t is taken outside common, v plus v naught, half into v plus v naught into t. Right. Okay, let it be double star. Now what you have to do is, you use the first equation v equal to v naught plus at and arrange for t and substitute that t here, you will end up with third equation. That is what I am going to do now. Okay, I will rub this. Okay, yes. First equation we have v equal to v naught plus at, correct? This implies, okay, I will arrange for t, okay, so a into t equal to, I will bring this side, that is v minus v naught, at equal to v, if it comes this side, okay, that becomes minus v naught. I want t, okay, that is therefore t, I will arrange for t equal to v minus v naught divided by a. Now substitute this, okay, substitute, okay, that triple star t equal to v minus v naught divided by a here, and you will end up with this equation in next step. Therefore this double star implies, okay, left hand side, x equal to half into v plus v naught, correct? X equal to half into v plus v naught into t equal to v minus v naught divided by a, v minus v naught divided by a. This implies x equal to half into v plus v naught into v minus v naught, or like this, I will write like this, 1 by 2 into a is taken this side, v plus v naught into v minus v naught. A is taken here, 1 over 2a, v plus v naught into v minus v naught. This is in the form a plus b into a minus b. You are all familiar with that, a square minus b square. So therefore I will write here this step, x equal to 1 over 2a into a plus b into a minus b, a square, that is v square, minus b square, that is v naught square. V plus v naught into v minus v naught will be v square minus v naught square. Okay, this is one. You just cross multiply. 2 into a into x, 2a into x, like this, cross multiply. Okay, 2a into x equal to 1 into v square minus v naught square, correct? Okay, I will bring this side. Okay, therefore v square equal to v naught square plus 2ax. Okay, v square equal to v naught square plus 2ax. Okay, when this come v minus v naught square, when it comes left hand side, that becomes plus. Okay, therefore v naught square plus 2ax will be equal to v square. So this is the third equation of motion. Okay, this is the third equation of motion, v square equal to v naught square plus 2ax. Okay, this is how we can derive the third equation of motion. Simple. Starting step same, till here same. Okay, then you are just splitting. In the earlier equation you have substituted v minus v naught as at, and you could able to obtain second equation. Don't go for that idea, don't use that step, you will end up here. So you just split and try to get this step, and finally you substitute the value of t equal to v minus v naught by a here, and just rearranging you will get the third equation, v square equal to v naught square plus 2ax. And this third equation can be derived easily using the same idea, graphical method. Area under the Vt curve represents displacement, but area under the Vt curve is expressed as area of the trapezium OABD. We are not going to split the area under the curve as area of the triangle plus area of the rectangle. This is not necessary. This is one simple way in which area could be calculated. Okay, if you want that, I can show you within no time. I can show you. Okay, same idea. Let me show if I don't know which method will be comfortable to you. This is the standard method. Okay, in NCERT you will get this. Okay, same idea can be used. Okay, same idea can be used in a different way. OABD is a trapezium. You all know area under the curve AB is nothing but area of the trapezium OABD, and you all know the formula for area of the trapezium. You will get the third equation easily. Okay, if you want, I can show you. Yes, area under the VT curve, that is area of the trapezium, area of the trapezium, area of the trapezium OABD, OABD, that is area of the trapezium. You all know half into formula, the sum of the two parallel sides, these two sides are parallel, OA plus BD into the perpendicular distance between them, or OD. The two parallel sides sum OA plus BD into the distance between them, perpendicular distance, not this. Okay, OD, half into OA plus BD, half into OA plus BD into OD. This is the formula for the area of the trapezium. You might have studied, okay, in your primary or elementary classes, high school classes. Okay, fine. Half into OA. What is OA? OA is V0 plus BD. BD is V into what is OD? OD is T. See, you have arrived that step. Okay, I wrote here. Okay, after rearranging. Okay, we got the same step, but here directly we are getting that step very easily. So this is area under the curve. You all know that is area under the curve is displacement. Okay, this implies. Okay, now substitute the value of T. Same idea, value of T from the first equation, V equal to V0 plus AT. So therefore T equal to V minus V0 divided by A. Substitute here. Okay, therefore half into V plus V0 into T equal to V minus V0 divided by A. Same step, A plus B into A minus B. You will get X equal to 1 by 2A into V square minus V0 square. Same repetition. That implies if you cross multiply 2AX equal to V square minus V0 square. Correct? Okay, so bring here, therefore this implies V square equal to V0 square plus 2AX. This is another idea using the area of the trapezium idea. You can write or you can derive the third equation very easily. So only 2 to 3 steps. V square equal to V0 square plus 2AX. This is how we can derive the kinematic equations for uniformly accelerated motion. We have arrived 3 important equations. Okay, V equal to V0 plus AT, X equal to V0 T plus half AT square, V square equal to V0 square plus 2AX. Simple equations which connects 5 important variables, V, V0, A, T and X. Okay, so this is all about this section. Actually, these equations were derived by considering the initial position of the body as x equal to 0 at t equal to 0. This is not the case always. So more general equations could be arrived. Okay, I am going to show you. I am not going to derive. Simple, just the modification of those equations will give you the more general equations for the general case. While deriving these equations, we have assumed that at t equal to 0, the position of the body was at x equal to 0. This is not the case always. That position may be non-zero. that is at t equal to 0, we have assumed that x equal to 0 while deriving these equations as a special case. Again, this is not the case always. That at t equal to 0, the position, initial position may be not equal to 0, say some x naught. Okay, say some x naught. Initially, the position was not at the origin, say at some initial position x naught. We can just modify these equations. We will end up with the more general equations for uniformly accelerated motion. Yes, we all know the displacement equal to final position minus final position minus initial position. This is the definition of displacement, that is delta x equal to x2 minus x1 in any case, correct? Initially, while deriving these equations, what we have considered, initially x equal to 0, that is x1 equal to 0, and after certain time t, x2 equal to, we have assumed x. Therefore, displacement delta x equal to final position x minus initial position. Therefore, displacement delta x is nothing but x. Initially we have expressed x as displacement, that is x minus 0 or x2 minus x1 equal to x, that is delta x displacement, when the initial position was assumed as 0. If that x is not equal to 0, which is equal to x naught, then for this case, what will be delta x? Delta x will be final position minus initial position, correct? Final position minus initial position. Final position is x after a certain time, and initial position is not 0, it is x naught. What is this? This is delta x. You all know what is this x? X is displacement delta x, correct? Now, to get more general equations, okay, for the uniformly accelerated motion with this consideration, we are going to replace x by, that is delta x equal to x by delta x equal to x minus x naught. In one word, you are going to replace x by x minus x naught in the equation, or in the equations you will get the general equations for uniformly accelerated motion. That is the first equation, v equal to v naught plus at. No change. Why? Because it do not consist of the displacement term x. No change. Second equation, x equal to v naught t plus half at square. You must replace x by x minus x naught. Earlier it was delta x. Now this is delta x. Displacement delta x must be replaced by x minus x naught. That's all. That is x minus x naught here. X minus x naught equal to v naught t. Other terms remains the same, no issues. You bring this side, x equal to x naught v naught t plus half at square. X equal to x naught plus v naught t plus half at square. This is second equation, general form. Okay, initial position at t equal to 0 was x naught, not 0. And third equation, v square equal to v naught square plus 2a into x. X is displacement. Displacement is here x minus x naught. This is the third equation. V square equal to v naught square plus 2a into x naught. This is the third equation. So this is how we can write the kinematic equations for uniformly accelerated motion. More generally, v equal to v naught plus at, x equal to x naught plus v naught t plus half at square, v square equal to v naught square plus 2a into x minus x naught. Okay. So this is how we can derive kinematic equations for uniformly accelerated motion graphically. We can derive the same equations, okay, same equations, general equations using the calculus method as well.